Welcome to this explainer. We are witnessing an absolute explosion in the growth of commercial electric fleets right now. But today, we're going to pull back the curtain and unpack the unseen, real-world, physical hurdles these fleets are facing on the ground every single day. We'll be looking at everything from the crippling effects of freezing weather on battery life, all the way to the incredibly complex, almost science fiction-level engineering required for autonomous robotic charging. If you want to understand what is actually happening behind the scenes of the EV transition, you're in the exact right place. Here is our roadmap for today. We're connecting the dots across some fascinating data, from tracking corporate market growth and the reality of temperature penalties, right through to exploring the highly technical, spacecraft-like docking protocols required for tomorrow's driverless robot taxis. Let's jump in. Section 1. The electric fleet boom. To really grasp the sheer momentum of this transition, we just need to look at a major player in the space. Check out this staggering number, 620%. In their 2022 annual report, commercial EV manufacturer Exos reported this massive revenue growth figure. And what drove it? A 525% increase in unit deliveries to major last-mile and regional return-to-base fleets. We're talking about delivering vehicles to heavy hitters like FedEx ground operators and UniFirst. This isn't just some small pilot program anymore. The massive commercial rollout is fully underway. Section 2. Weather versus electric vehicles. Because as these massive regional and last-mile fleets actually hit the streets, they immediately collide with a very physical, unavoidable reality: the weather. A comprehensive study by AAA put these vehicles on laboratory dynamometers, which are essentially giant treadmills for cars, and the results revealed a pretty stark contrast. While operating in hot weather at 95 degrees causes a modest 10.4% efficiency drop in EVs, freezing 20-degree weather is a completely different story. And the cold, efficiency absolutely plummets by over 35%, and calculated driving range gets slashed by 39%. So Fleet Manager in a cold climate is dealing with a drastically different operational reality than one in a temperate zone. Section 3. The hidden temperature costs. This dramatic loss of efficiency in cold climates goes way beyond just range anxiety for drivers. It translates directly into hard dollars and cents. Just look at the massive penalty when you leave the depot at 20 degrees Fahrenheit. If a fleet relies on their own home-based charging infrastructure, the cold adds about $32 per 1,000 miles. But if they're forced out onto the road and have to rely on higher-priced public infrastructure, operating an EV in the cold costs an additional $76.93 per 1,000 miles compared to moderate temperatures. This massive cost penalty heavily incentivizes commercial fleets to build and rely on their own return-to-base charging systems. Section 4. The driverless charging problem. So we know fleets must charge efficiently at their home base, but what happens when we completely remove the human from the equation? As we look toward a future dominated by autonomous fleets, a massive, often overlooked logistical hurdle emerges. It's a simple question, right? How do fully autonomous fleets charge without human hands? Well, current EV charging protocols like ISO 15118 and the NACS standard fundamentally assume a human is standing right there. They assume you and I will physically align the car, grab the heavy cable, plug it in, and authorize the payment. That fundamental assumption entirely breaks down for driverless robotaxis like those from Waymo or the upcoming Tesla Cybercab. Section 5. How autonomous charging works. To solve this missing human element, researchers have proposed a brilliant multi-layer protocol stack called ACAP. That stands for the Autonomous Charging Alignment Protocol. ACAP is designed to orchestrate the entire charging lifecycle completely without humans. It's broken down into 4 distinct phases: discovery and reservation, approach and alignment, connection and charging, and departure and settlement. And what's incredible is that this protocol pulls the average charging session overhead down to under 45 seconds, literally from the exact moment the robotaxi enters the bay to the moment high-voltage energy actually starts flowing. 45 seconds. But how does a driverless car actually get the plug perfectly into the port? Well, the researchers note that Phase 2 utilizes, and I quote, a 3-stage positioning cascade inspired by the International Docking System standard used in spacecraft rendezvous. That's right, we're looking at how borrowing mechanics directly from the International Space Station actually works in a parking lot. It works like a funnel. It starts wide with Stage A, the course approach. Here, the vehicle uses 5G or vehicle-to-infrastructure side-link beacons, basically specialized digital radio signals broadcasted by the charger, to navigate to the general charging bay entrance. At this stage, the vehicle's accuracy is between 1 to 3 meters. It just gets the car in the right general driveway. Next comes Stage B, precision guidance. The vehicle now locks onto the charger's ultra-wideband anchors to triangulate its position. The autonomous driving stack executes a parking maneuver to guide the car to within just 10 centimeters of the perfect target pose. The funnel is getting much tighter now. Finally, we reach Stage C, fine docking. Once the car is parked, a robotic arm takes over. It utilizes structured light vision and highly sensitive force-torque sensors to achieve a sub-millimeter connector insertion without damaging the vehicle's charge port. If it senses too much resistance, it stops, ensuring the robot doesn't aggressively scratch the paint job. It's a perfectly orchestrated robotic handshake. Section 6. Securing the driverless future. Because physically plugging the car in is really only half the battle. When a computer is doing all the driving and the charging, how do you verify the charger it just pulled up to isn't actually a malicious trap designed to hijack data or drain a fleet's wallet? To ensure an autonomous car isn't lured to a rogue station by hackers broadcasting fake 5G signals, the ACAP system employs something called cryptographic spatial anchors, or CSA. This vital security mechanism requires the vehicle and the charger to essentially solve a two-way mathematical puzzle, proving to each other that they are physically within 15 centimeters of one another before any transactions occur. It cryptographically binds their authenticated identities to their real-world physical locations, stopping spatial spoofing dead in its tracks. The depths of the fail-safes built into this protocol is just incredible. For instance, if an attacker tries to use signal jamming, known as a broken wire attack, ACAP is designed to detect the interference and safely pause the power, rather than abruptly aborting, which can cause high-voltage safety issues. If the robotic arm jams, there are hardwired physical emergency stops entirely independent of the software. The whole protocol is meticulously designed to fail-safe under extreme adversarial and mechanical stress. As electric fleets scale massively, and as vehicles inevitably lose their human drivers, this brilliantly engineered transition from human hands to robotic, spacecraft-style docking will be the quiet, unseen backbone defining the future of transportation. It's an incredible engineering challenge. Thanks for joining me on this explainer. I'll leave you with this to think about. The technology to build autonomous robotaxis is already here, but are our infrastructure protocols truly ready to securely plug them in?